Welcome to yet another video on SRID Cloud. In this video, we are going to talk about OpenShift Container Storage. You can refer to my earlier videos in this same channel. I produced several videos on Ceph, how to deploy Ceph on bare metal, and also how to deploy the same on Kubernetes. I also described how to use the Ceph storage, both block and file storage, onto your application workloads on Kubernetes in separate videos. So refer to all of them. But this is another logical extension in the same series. The Red Hat company has implemented the Ceph storage on OpenShift using OpenShift Container Storage. So this is nothing but a wrapper around Ceph and Rook and all that. And on top of block and file storage, Red Hat has already added Nuba component to OpenShift Container Storage so that object storage can also be realized. So your application workload can now enjoy persistent storage in block storage format, file storage format, and also object storage format. Ceph is already an object storage based distributed storage system, but it is the Nuba is required to realize it from object storage perspective. So now let's get started, and I will describe how to deploy OpenShift Container Storage onto your OpenShift Container Platform and how to verify and all that. So before that, let us have a quick conversation about the Ceph itself. The containers are enjoying the ephemeral storage offered by Kubernetes under the covers, so that the containers can be started and they can be in a runtime mode. And on the worker nodes, the Kubernetes environment also provides some logging facilities and all that. So the containers do not have persistent storage built in them unless you create a separate persistent volume claim and attach it to it. And then you can, the application workload running under your pod can read data from the storage, and you can write data into storage, and it can be made available across the instances of the container under the Kubernetes or OpenShift environment. So there are several options available for you to implement such a persistent storage for your application workloads. And the most primitive or most popular one is NFS. So you can set up the NFS storage, and then using the NFS client, you can make the persistent volume and persistent volume claims out of the NFS storage, and you can attach the persistent volume claims to your application workload. And then your workload will start using the NFS as a persistent storage. The second important implementation is using the CSI. I have made a separate video on CSI and how to develop a CSI driver and all that. Refer to that video, it is very detailed. So if you have a storage backend, you can develop a CSI implementation for it and install it on your OpenShift or Kubernetes environment. Then you will be able to create persistent volumes and persistent volume claims and attach the persistent volume claims to your pod and all that. So many storage vendors have developed their own CSI implementations, and they are made available in the open source, and you can use them already. So now what is the OpenShift Container Storage then? OpenShift Container Storage also has a CSI implementation built in it. So the way Ceph storage is brought into Kubernetes through OpenShift is using a bunch of CSI drivers. So these CSI drivers are all installed automatically for you when you install OpenShift Container Storage. I'm going to show you all the pods, CSI pods particularly at the end of this video. So OpenShift Container Storage is a very robust and it is highly scalable. It is very reliable storage option for your application workloads. And on top of that, the best Kubernetes implementation available to this date is OpenShift Container Platform. So OpenShift Container Platform with OpenShift Container Storage is the best optimized solution available for you today for application workloads, persistent storage purposes. And there are a lot more other options available, and you can Google around, and you can even go to Kubernetes documentation and find out what other options are available for persistent storage for your application workloads. There are quite a few of them. So now let us have a quick look at the Ceph. As I said earlier, I made a separate video on Ceph itself. Rook is the orchestrator of Ceph, and Ceph and Rook together, they use the CSI framework as I mentioned earlier, and that is how the Ceph storage is made available to the containers in the Kubernetes or OpenShift environment. So now let me briefly talk about the environment that I work on to implement OpenShift Container Storage on IBM's Power Platform environment. But whatever I'm going to describe need not be specific to IBM platform. It can be applicable to any other processor platforms, wherever it's applicable. So the environment that I created and I work on generally is based on IBM Power processor platform. The Power 9 and Power 10 are the latest versions of the Power processor systems. So using various other solutions, I deploy the OpenShift Container Platform. So I generally create 3 master nodes and 3 worker nodes and 3 storage nodes. And so there are 9 virtual machines created. And out of those 9, 3 of them are marked for control purposes, that is master nodes. And 3 of them are dedicated for OpenShift Container Storage. And then the remaining 3 are dedicated for my application workloads. This is the recommended environment for you. But if you're running short of resources, you can combine the storage nodes and worker nodes together. The minimalistic environment can be 3 master nodes and 3 worker nodes. And those 3 worker nodes can act like storage nodes as well. But either way, you can implement the OpenShift Container Platform as mentioned here. And the most importantly, the storage nodes, whether they are standalone storage nodes or combined with worker nodes, it doesn't matter. They have to have an additional storage, a data volume attached to them. In my particular case, the IBM Power system are connected to a SAN storage backend through SAN switches, and the volumes are provisioned on the SAN backend and they are mounted on the worker nodes. So if I log into one of the worker nodes and then run a command called lsblk or lsblk-f, I should be able to see the extra data volume with nothing on it. There should be no file system, there should be no, it should not be even formatted, it should be a raw block device. And such a storage device attached to the worker nodes is the first step to implement OpenShift Container Storage. But having said that, you may Google around and then you may find that there are other environments where this is not really needed. Really needed in the sense, need not be a SAN connected storage onto the worker nodes. For example, in the VMware or AWS or Azure environments, the storage can be separate. When you deploy OpenShift Container Platform on those environments, you can create the storage separately. And generally, there will be a storage class associated with that particular storage. And that storage class can be used to deploy OpenShift Container Storage directly. But otherwise, let's get back to the environment that I'm working on, the IBM Power Platform with SAN attached storage. The lsblk command is used to make sure the extra storage, the additional storage, is attached to the worker nodes. So that is the environment that is needed for this particular presentation. So think of the, even though the storage is attached through SAN, the lsblk command output will show as if there is local storage available on the worker nodes. So they are realized through SAN connectivity, but ultimately they are looked upon as if there are local storage on the worker nodes. So the steps involved in this particular case is to label the storage nodes first of all, and then you have to implement what is called local storage operator, and then create the local volume objects or local volume set objects that in turn will create the persistent volumes out of the local storage attached to the worker nodes. And then you go and create the storage cluster. So we're going to see the exact steps needed with examples to accomplish all these three things. So in my environment, I have 6 worker nodes and 3 master nodes. And I decided to implement OpenShift Container Storage onto the worker 0, worker 1, and worker 2 worker nodes. And then I will use the worker 3, 4, and 5 to deploy my application workloads to consume the OCS storage. So these storage nodes, as I said earlier, will have 2 storages attached to them, each of them. One is a boot volume, the other one is a data volume. The boot volume will carry the operating system needed for the storage node, the Red Hat CoreOS operating system generally. And the data volume will be empty. If I, as I said earlier, if I run lsblk-f command on these storage nodes, I should be able to see the additional disk with nothing on it, with no file system or even format mounted on that particular device. So the command used for labeling the worker nodes is mentioned at the bottom of this page. The OC label nodes worker 0. The same thing will be repeated for worker 1 and 2. And then cluster OCS OpenShift IO, OpenShift -storage as the key with the value empty string. So this is needed for the OpenShift Container Storage operator later on to identify the worker nodes on which the pods will be placed. So with this done, the next step is to create a namespace for local storage. As I said earlier, the local storage operator is optional. In my case, I need it because the storage is local and it is attached to the worker nodes and it is made available through SAN connected environment and so on. But in your case, you may not have to do this actually. You can directly go to the storage cluster creation if the storage option, the storage persistent volume for OCS, the OpenShift Container Storage, is made available in some other path. There should be a storage class associated with it. So in my case, I need to deploy this local storage operator. So because of that, I have to create the OpenShift local storage namespace. So using the YAML mentioned here in this page. And then I would create an operator group for the local storage operator that I'm going to deploy, and then a subscription. And in the subscription, I mentioned the channel name. For this video, it is 4.8. That is the last released OpenShift container storage in production right now. And most importantly, the install plan approval has to be set to automatic so that the operator will get installed automatically without any manual intervention. So now with the local storage operator in place, the next step is to create a CR, and that is the local volume. So when this local volume object is created, the local storage operator will wake up and will go and detect the extra storage attached to the worker nodes and create persistent volumes for them. So here is a YAML file for the local volume object. There is a mention of the worker node names, worker 0, 1, and 2, and also the device paths. So dev SDA and dev SDC are the two storage data volumes attached to each worker node. So if I log into, say, worker 0 and then run the lsblk -f command or lsblk command, I should be able to see dev SDA and dev SDC as two empty block storage devices attached to them. And the size of these two devices have to be uniform across the worker nodes. For example, if SDA is 100 gigabytes, then there should be a 100 gigabyte SDA device on worker 0 and worker 1 and worker 2. And if SDC is 500 gig disk, then it has to be the same 500 disk on all worker nodes. So for this particular example, I attached two 500 gig disks on each of these worker nodes. So they are SDA and SDC. And refer to the storage class name mentioned in this YAML file. It is local block. So this is very important. This will act like a bridge between the local storage and the OCS, the OpenShift Container Storage operator later on. So when I run this particular YAML file and when I create the local volume into the OpenShift environment, I should be able to see the CSV, the operator framework object. It should be in succeeded state. And also, I should be able to see 6 persistent volumes, 500 gigabytes each. And their storage class name should be local block. And also refer to the access modes. They're all read, write, and then own, so that application workloads through Ceph or OCS will be able to not only read but also write to Ceph storage. So make sure these two are properly seen when you run the OC get CSV -n OpenShift local storage namespace or OC get PV. You should be able to see this output. And you can attach as many storage devices as possible to your worker nodes. You need not have to stop with only 2. And also the number of worker nodes need not have to be 3. The minimum is 3 because to have the quorum in the cluster, you have to have 3 minimum worker nodes or storage nodes, I should say. You can go up to hundreds as Ceph is capable of handling such a large scale. So now, after creating the local storage operator and the persistent volumes through it, the next step is to get into the OpenShift container storage operator. For that, I should create the namespace first of all. And while creating this namespace, OpenShift storage, I generally add another label called cluster monitoring and set it to true. So this label is used by the OCS operator code to place monitoring pod on the appropriate worker nodes. The next step is to create the catalog source and the operator group as well, and refer to the registry, the image for the catalog source, redhat.io, Red Hat operator index, and then version 4.8. So this will change in future when you deal with the futuristic or future versions of OCS. So when this is completed, the final step is to create the subscription, and that is done with this particular YAML file. Make sure the channel name is appropriately mentioned, stable 4.8, and you refer to the source of the subscription as OCS catalog source, the one that we created in the previous step. And if you're interested to further debug, if you run into any problems, go and look at the pods created under OpenShift Marketplace namespace. And all of them should be in running state after creating this particular subscription. And if any of them are in the error state, then you can debug by looking at the logs and also the description of the pod objects. So now when this is completed, you should be able to see some pods in the OpenShift storage namespace. These are the operator specific namespace objects, pods actually, and all of them should be in running state, and there should be a CSV in OpenShift storage namespace that should be in succeeded state, and the storage class that I mentioned at the bottom of this page is coming from the local storage operator work that we did a few minutes ago. So these three are needed to proceed further to create the storage cluster or OCS. And that is done with this particular YAML file. So I want to apologize for the format of these YAML files mentioned in this presentation. You may want to add appropriate formatting for them, but you know YAML structure, so you should be able to do that. So this is the storage cluster YAML file, and the most important aspects of this particular YAML file is the storage device set. Here I mentioned the count as 2 because I added 2 storage devices to every worker node. But this number has some significance, and the formula used to arrive at this number is mentioned on the sides. You may have to delete that formula when you actually use this YAML file. So the number of storage nodes, the count is equal to the count is equal to the number of storage nodes multiplied by number of persistent volumes per node. So when we saw earlier, we saw 6 persistent volumes out of 3 worker nodes. So that number is 2, and then divide by the number of nodes. So 3 times 2 divided by 3 is 2. That is the formula used to calculate the count of storage device sets. So that's why I mentioned 2 there. And then if you look across on the other side, there is a property called replica, and it is set to 3 because 3 is the default value. 3 is the minimal value for the replication. So what that means is your data will be replicated into a 3-way cluster. And back on the left side, the bottom last property, the access mode, make it as read write once. And everything else is self-explanatory. But I forgot to mention, on the right side, you can see the storage class name, local block. So this is the storage class that got created when the local storage operator was implemented, and then local volume was created. All the PVs that we created were using the local block storage class name. So the moment you create the storage cluster, you should be able to see the CSV, the OCS operator CSV, turning into installing from succeeded state. And after a few minutes, it will go into the ready phase. That means the entire OpenShift container storage software is properly installed. If not, then you may want to debug and see what is going on by looking at the pods and their statuses in the OpenShift storage namespace. And also, you can query the storage cluster itself. To begin with, the phase will be progressing, and after a few minutes, it should convert into succeeded state. So now I want to show you the pods created by OpenShift Container Storage under OpenShift Storage namespace. And needless to say, all of them should be either completed or should be in running state. So here is the first set, and you can see the first quite a few of them are CSI driver pods, and you can see three Ceph file system plugin pods, one for each worker node. And similarly, the block storage CSI driver RBD plugin is also out there in the running state, one on each worker node. And then there are a couple of file system provisioner and the block storage provisioner. If you look at my other video on CSI, you will be able to understand what these pods are and what kind of services are offered by these pods. Just to summarize, these pods contain the actual code needed to create volumes, delete volumes, attach volume to a particular worker node, unmount it, and attach the same to pods wherever it's needed. Whenever you create a persistent volume claim and attach the persistent volume claim to the worker load, the application workload pods. Refer to that video. It's very detailed, and you should be able to understand that. And then there is Nuba core and Nuba DBPG0. These and the Nuba endpoint and the Nuba operator. These four parts offer the object storage implementation. And here is the second set of parts, and the OCS operator pod, the second one from the top, is the mother of all parts in this particular category. And then you can see a bunch of MDS parts. These are the metadata service for the file system offered by OCS. These two parts run on two of the three worker nodes. And then there is a manager pod running on one of the worker nodes only. And then there are three monitor pods running on each of the worker nodes. So these pods provide the backbone for the OpenShift container storage. These are the Ceph implementations. And here is the final set. The OSD pods, the second, third, and fourth, are the most important pods. They run on each worker node, and they are the one who manage and maintain the worker node specific storage for Ceph. And if any of them is not running, then there is a problem, and that means that particular worker node is not contributing to the OpenShift container storage. It may happen if the entire worker node goes down for some reason, or if the worker node is terminated for maintenance purposes, then you should see the corresponding OSD pod going into error state or terminating state. As I said earlier, 3 nodes are minimum. So if you deploy a 3 worker node based OpenShift container storage, and if one of the worker node is down, then the cluster will not be useful at all. And the OSD prepare parts are in completed state. And see, these are the parts that create the OSD parts. And finally, the RGW, the RADAS gateway pod, offers the object storage and the fundamental layer of Ceph to the OCS. So make sure all these parts or in running state, and or in completed state. So this means the OpenShift container storage is properly implemented, and now it is ready for consumption. Alternatively, or I should say optionally, you can create what is called a Ceph toolbox using the commands mentioned in this particular page. Using the OC patch OCS initialization, you can enable the Ceph toolbox pod. After running the OC patch, you can run the OC get pods in the OpenShift storage namespace and identify the rook Ceph tools pod. So whatever I mentioned in the last line in this presentation file, a page I should say, is an example from my implementation. So you may see something else. So then you can use the OCRSH command to get inside the pod and run any Ceph command that you know. So Ceph -s will give you the health of the Ceph storage, for example. You can get a listing of all pools, and you can do quite a lot. If you know Ceph, then this is how you can run those Ceph commands in this environment. So when you run Ceph -s, like I said earlier, the output will look something like this. The health has to be health_OK for you to proceed to consume this implementation. If it is health error or health warning, then you should debug this environment and then see why the health is not okay. Sometimes if you have some disruptions, for example, one of the worker node went down and then it is brought back, it'll take a couple of minutes for the health to get to OK state, because the OpenShift container storage, which is Ceph under the covers, will take some time to rebalance and make sure the storage is replicated properly across the nodes and so on. So in that case, you should see a progress somewhere in this output. If you repeatedly execute this Ceph -s command, you should be able to see the cluster recovering. So now, after implementing the OpenShift container storage, how do I use it? This is very common across the Kubernetes environment. The OpenShift container storage will create the appropriate storage classes. The second one in the list is for block storage. The third one is for the object storage. And the fourth one is for the file system storage. So using these storage classes, you can create persistent volume claims of desired size. And then you can attach those persistent volume claims to your pods. And refer to my earlier videos on Ceph on Kubernetes. And also I created a couple of useful videos how to consume Ceph on Kubernetes for block storage purposes and then for file storage purposes. Refer to those videos on how to use these storage classes. They're very straightforward. Once again, take this storage class. So for example, if you want to create an application workload persistent storage for block storage, then create a persistent volume claim with OCS storage cluster Ceph RBD as the storage class name, and then attach it to your pod when you create your pod YAML file. So this is how you can deploy OpenShift container storage on OpenShift Container Platform. And as I mentioned earlier, the local storage operator is optional. It is needed in my particular case for IBM Power environment, but in your case, you need not have to do that. And everything I mentioned in this presentation can also be done using user interface, the OpenShift Container Platform user interface. But generally, when you go through user interface, you don't have much control. You just click here and there and then click to the next page and so on. The local storage operator will get installed, the local volume will get installed, the persistent volumes will be created under the covers for you, and then the storage cluster will get created for you. But by going through this CLI option, you will know more. That is the reason why I choose to do it using CLI to present OpenShift Container Platform on OpenShift Container Storage on OpenShift Container Platform. So, hope you enjoyed this video. Hope you learned about OpenShift Container Storage, or if you are familiar with Ceph, then you should get excited to see the availability of Ceph storage on OpenShift Container Platform. So I intend to produce more videos in future to talk more about OpenShift Container Storage, particularly the object storage aspect of it. My probably next videos will talk about how to use the OpenShift Container Platform and OpenShift Container Storage for hybrid cloud. You can dynamically push data from your private computing or private cloud computing into public cloud like AWS or IBM cloud or and so on. So look forward to those videos in a very short time from now. So have a wonderful evening, or wherever you are, have a wonderful day, and bye for now.